Okay, so let's go to the start of my talk. Right. Okay, so the title of my talk, Minimal Logics for Incompleteness. I gave it a subtitle, A Personal and Biased Journey Through the Landscape of Incompleteness. So what will I do in this talk? Well, first of all, I'd like to thank the organizers and congratulate them for organizing such a nice talk with prominent names, and in that sense, it's an honor to be among those. So thanks and congrats. And so what will I do? I will look at various logics inspired by Gödel's incompleteness theorems, and then I will see how much we can, of those well-known logics, we can throw away to still do stuff with these logics. So that's why we speak of minimal logics. This minimal is a non-precise sense, and it's merely to indicate they're small, and I think they're very small, and I think they're minimal. It's non-precise. Okay, so the nice thing about preparing this talk is when a conference has a theme, then it makes you reflect on how much of your work can be viewed as being part of this theme. And in particular, preparing my talk made me realize how much of my work really go back to the incompleteness theorem. But maybe that has to do also with Matthias Baas's remark that even though Gödel is sometimes mistakenly taken as the founding father of logic, he is not, but certainly he's one of the founding fathers of modern logic. Okay, so first a disclaimer: the content of this talk is not only just selected on the importance of the results to the field, but largely reflects my own wanderings through the landscape of incompleteness and what I found there. Okay, so then I'd like to steal more of your time before I get started. I want to make an announcement within the Proof Society. We have this yearly season school, well, summer school or winter or whatever school, and associated workshop. Due to COVID, this was postponed last year, but this year, as you may have heard already, we will do it, and you can find more information at the website of the Proof Society, and it will be held from November 29 to December 3. And well, if that's not already an excuse, it's in Madeira. So I think that's a first conference after COVID in situ. It will not be streamed. That's a good place to be. Okay, so now what will I do in this talk? So as I told you, I will speak of logics for incompleteness. Then I will speak of the basic logics, and then I will speak of generalizations of logics that have more applications and can deal with generalizations of Gödel's incompleteness theorems. Then I will speak of the positive part of incompleteness. If you know a general way of getting incompleteness, then you can have a general way of completing things through this incompleteness results. So that is what I will talk about in that part, in the last part. And the final part will deal with minimal logics. So logics which are really small and optimal in a sense. So that's the program. So let's start where it all starts. And those are Gödel's incompleteness theorems. So without entering in technical details, the first one says that for any consistent axiomatizable theory, T of some minimal strength, there is a true sentence that is not provable in T. And most important to this conference, I think, is the second incompleteness theorem, which says that if I have such a consistent axiomatizable theory T of minimal strength, then T will not prove the arithmetical sentence conti, which in a sense, which has been discussed in various talks on intentionality here, naturally expresses the consistency of T. And if T, moreover, is slightly better behaved than merely consistent, for example, omega consistent sound or just sigma 1 sound, then it will also not prove the negation of the consistency, so the inconsistency. So logics. Now these are the theorems. Now let's move to logics. So why would we need logics to speak about this, right? Well, one way I think is to better understand the dynamics behind the theory, the theorems itself. So first, to settle the language, well, we have seen in the formulation of the incompleteness theorems, the notion of provability is really central there. And Gödel himself already suggested that that we can collect facts like theorems, lemmata about this operator of provability, and then theorems can be reasoned in a modular way by referring to some standard lemmata, which will just be modal axioms, right? So it's natural to consider a language which in the signature has box for provability in T. And Gödel gave such a predicate that indeed a sigma 1 predicate that holds only true on Gödel numbers that indeed are provable, are Gödel numbers of formulas provable in piano arithmetic. And moreover, the predicate has various other good properties that we will touch upon later. Good. If we have such a language, then at least we can denote the Gödel's second incompleteness theorem, which we see here. If so, diamond is the jewel of the box, which if box stands for provable, diamond would stand for consistency, and then we can formulate Gödel's in a second incompleteness theorem in a sense. In this signature, we say if I'm consistent, if a theory is consistent, then it's not provable that it's consistent, right? But of course, expressibility of a theorem is not merely enough for motivation to introduce and study logics for them. Things change if we have a class of statements. And I think this is a good way to start and motivate the logics. And there's this problem stated by Friedman, like, okay, here we have this second incompleteness theorem. Can we give it a characterization of all provable combinations or generalizations of this, so Boolean combinations of iterated consistency statements? Can we and iterations thereof? So can we find a good characterizations of the provable sentences, or for that matter, the provable ones? Note that by the properties of the provability predicate, the provability question can be reduced to truth, since a closed formula is provable in piano arithmetic if and only if on the natural numbers the boxed version of that is true. So it's enough to consider truth on the natural numbers, the standard model of the natural numbers of those formulas as isolated by Harvey Friedman. And so this question, we need actually, and we will come back to that, a closed fragment is sufficient. So if we have just falsity, implications, and box formulas, then we can in this language we can cast this question of Friedman's. And then Boulos and independently Van Bentham could prove in a logic, so a collection of theorems that generate provable and true provability principles, that any sentence A in this signature is equivalent, using these lemmatas collected in this logic, to a Boolean combination of formulas of the form box to the n falsum, right? And then of course our problem is settled because we know that they are false on the standard model of arithmetic, right? Boulos calls this the first mathematical application of modal logic, right? So we reason in modal logic, and we don't even need completeness for this modal logic, because at the time Boulos and Van Bentham obtained this result, there was no completeness around. So with soundness alone, we can get a genuine, well, mathematical or meta-mathematical result, and arguably, this is the first one. At least this is what Boulos claims. Okay. So logic. So this is already a first motivation why introducing logics. Another motivation is, well, we can study the dynamics that explains the incompleteness theorems. And for example, the lemmata, so to say, right? We can view this as lemmata when you see it as the arithmetical counterpart of these modal logical statements. Then we know that the Hilbert-Bernays-Loeb conditions are, in a sense, enough or minimal in some sense to get the second incompleteness, the reasoning towards the second incompleteness theorem going. There are other requirements, and well, there are people in the audience who know much more about this than I do. But this is another reason to introduce modal logics that speak about the incompleteness phenomena. Right. So what are those logics? Well, as I told you, there's much reasoning going on with this provability predicate. So, for example, right, Gödel proved his second incompleteness theorem by considering a formula that says of itself, lambda is a sort of liar sentence, I'm not provable. And then if Peano arithmetic proves that certain sentence is equivalent to its own non-provability, then it is equivalent to the non-provability of 0 equals 1. And this in turn can be seen as a form of reflection. So, right, the negation is the same as provable. From the antecedent, I can prove something false, for example, 0 equals 1. And now we can write this consistency statement as a form of reflection. So lambda, the liar sentence that Gödel considered, is a particular instance of reflection. If provable, then true, right? And since lambda, by Gödel's ingenious reasoning, is not provable, we can show that this particular instance, one of the simplest instances of reflection, is not provable by Peano arithmetic. That if Peano arithmetic proves 0 equals 1, then 0 indeed equals 1. Of course, this is important that Peano arithmetic speaks about its own provability, because, for example, ZFC can prove this reflection. Right. So I want to stress that this probability predicate that we have is sigma 1 complete in a very precise sense, right? That is to say, for each computably enumerable set A, there is an arithmetical formula that, if I put that arithmetical formula under the box, then this box formula, I don't know if you can see my pointer, but the box PA of this row A n, that exactly defines the set A. And moreover, I can find this row uniformly from an index computing A. So in that sense, the provability predicate is sigma 1 complete, and thus at the outset, it's not clear that we can collect in a nice and satisfactory manner all the principles that govern this sigma 1 complete predicate, right? What do we mean capture all the behavior that is that is exposed by this predicate? Well, that is what I want to make precise in the next 2 slides. So we have, for example, seen that piano arithmetic does not prove this particular sentence, right? This instance of reflection. However, this instance of reflection is provable. If 1 = 1 is provable, then 1 = 1. Yeah, of course, this is provable because piano arithmetic can prove 1 = 1. And then, of course, Loeb's theorem says that actually piano arithmetic can only prove reflection when it does so trivially, right? So if it proves an instance of reflection for itself, then it is in virtue of the antecedent, the consequent being provable, right? And the formalized Loeb's theorem is actually provable in piano arithmetic, and this holds for any sentence A. So it's this finding logics is abstracting away from instances, right? Being closed under substitutions. So that is what we're after. And so how will we characterize all the provable structural properties? We do that in 2 steps. So first we devise this modal language, which we do here in this the box language, where we have formulas formed by box, falsity, and Boolean operations. And then we relate these formulas somehow to formulas in piano arithmetic, which we have already seen that we do that by mapping the box to this sigma-1 complete provability predicate, and mapping propositional variables to arithmetical sentences, arbitrary arithmetical sentences, right? And in this way, we can say that, for example, this distribution axiom that if P implies Q is provable, then the probability of P implies probability of Q. That is true for any realization, right? And that is regardless of the realization. So that's what the game of logics is. We define the probability logic of a particular theory as those sentences in the model signature, such that for every realization, they are provable in the theory. And right, ignore that. And I want to stress that a priori, this has a Pi2 definition, right? Because here is a quantifier for all realizations. And then we say there is a proof, right? So this is Pi2 quantifier alternation. But we can do much better in this case, right? We know that Gödel-Loeb's logic does the job and characterizes this probability logic, and it's as we all know, or most of us know, it's the axioms of this unimodal propositional modal logic is given by all classical tautologies in this signature. So not only do we have P or not P, but we have also this tautology in under substitution instances, for example, box P or not box P, etc. And then we have all distribution axioms and instances of Loeb, and the rules are modus ponens and necessitation. So if I have a proof of A, then I have a concrete object, and then the theory can check that this proof is indeed a proof. So then I have the probability of A, and it's those rules that that define this logic GL. And Solovey proved that indeed this characterizes exactly all the structural provable behavior of the provability predicate in this sense of the completeness theorem. So GL proves phi if and only if phi star is provable for any arithmetical realization. Okay, so I want to stress, because later we make the move to quantified provability logic, that prima facie it would be Pi2, this logic, but we have actually a logic which is much simpler, and it's complexity p-space complete, as we know. So that's good. Now, that one can play the same game as for true provability logic, we have already seen that piano arithmetic does not prove reflection for the sentence 0 equals 1. However, it is true, right? It is this reflection principle. And on the natural numbers, that is true. And we can have a p-space logic again, generating all true principles, which is GLS, S for Solovay. And it's axiomatized by all theorems of GL, and then adding the reflection principles. Box A implies A, and modus ponens is the only rule. And this generates all the always true principles of provability logic. Good. Now let's look at some. So these are the main logic that govern the behavior and explain the behavior of the provability predicate and some of the dynamics behind the second incompleteness theorem. So now I'd like to look at some generalizations of this. So, well, the first one is not a surprise that I will look to interpretations because, being a student of Albert, I've worked much with them, and one issue that one can expect is that, well, maybe a theory cannot prove its own consistency, but maybe he can somehow, by reinterpreting the essence of what consistency means, a theory can interpret its own consistency. And well, interpretations are around abundantly in mathematical and meta-mathematical practice. And we will write this symbol, this triangle A, U interprets V, is written as such. And that means that there is some translation such that any theorem of V becomes a theorem of U under this translation. And of course, the translation should have some good properties, not mapping everything to the same tautology, for example. So it should preserve some structure, etc., right? But this is the idea. So think of the interpretations that you use in logic, mathematics, and that's basically what's going on here. And then Pfefferman proved that indeed Gödel's incompleteness, second incompleteness theorem can be generalized in the sense that if U interprets the consistency of U, right, then U itself is not consistent, right? So if we equivalently, we can say if a theory is consistent, it cannot interpret its own consistency. So which is, it doesn't come as a surprise, but I think it's nice to mention in this sense. Also, I think it's nice to mention that interpretations give us a positive flavor to Gödel's second incompleteness theorem. So the consistency is not only not provable, but in a positive sense, we can always, for this large class of theorems, we can interpret the inconsistency. So it's a stronger and more constructive statement than the unprovability of consistency. We can interpret the inconsistency in a theorem. And this is also expressible in this language of interpretations. And the same game that we played to get provability logic, that can be done with interpretations yielding interpretability logics. So interpretability logics are less stable than provability logics. So Solovay's theorem that Gödel-Loeb's logic is the provability logic for piano arithmetic really can be generalized to tons of theories. So basically any theory that incorporates somehow elementary arithmetic and is sigma 1 sound will have Gödel-Loeb's logic as its provability logic. The situation is different for interpretability logics. So to show this, we first carve out a core fragment of the logic, which is IL, as introduced by Visser, and it says that if B follows from A, provably, then by the identity interpretation, a theory together with B will be interpretable in the theory together with A. That's this axiom. The second axiom says that I can compose translations to get a composition of interpretations. And so if A interprets B and B interprets C, then A interprets C. Here, A and B are sentences which we add to a certain base theory T, right? And this axiom should not come as a surprise. This axiom says that we do, that we can make choices. So if I have an interpretation of A, of C in A and also of C in B, then depending on whether I have A or B, then I pick either the one or the other translation, and this gives me an interpretation of C. Interpretations have been used for relative consistency proofs, and this is expressed by this axiom. So if B is interpretable in A, then the consistency of B can be reduced to the consistency of A. And this can be viewed as the fact that, if I know the consistency, then I can uniformly squeeze out the consistency of A of T plus A, then I can make define internally a model of T plus A. So that's this axiom, right? And as before, we can now define the interpretability logic of a theory, and that is well, just copy paste, right? Here there's a typo. It should not be the language with only books. It should be the language with box and this triangle, right? So so any formula in this language is in this interpretability logic of a theory T if T will prove all the arithmetical translations, where now box is mapped to, again, the provability predicate, and the triangle is mapped to a natural arithmetization of interpretability. Right. Independently, Shavukov and Berarducci could establish that that piano-arithmetic, the interpretability logic of piano-arithmetic, is this basic logic IL, together with the axiom scheme that if A interprets B, then A and box C interprets B and box C. And this is called Montagna's axiom, and the logic is often referred to as ILM. But prior to this result of Shavukov's and Berarducci, Visser proved for finitely axiomatizable theories like I sigma 1 that those theories have an interpretability logic which is characterized by this axiom that says if A interprets B, then it's provable that A interprets B, right? It should not come as a surprise because, A interprets B really says there is an interpretation such that for all theorems of the theory T plus B, it was also a theorem of T plus A. So a priori, that's sigma 3. But if you're finitely axiomatizable, you can get rid of this for all theorems, because if you can prove that just the translation of the axioms are provable in the target theory, then that is sufficient. So then interpretability becomes a sigma 1 notion, and by sigma 1 completeness we get this axiom, and Visser proved that this is sufficient in this context. So and this is the logic ILP. If you have some space left in your temporal memory, please store the names IL, ILM, and ILP, since they will come back later. Now, so that's why do we talk about this? Well, because these interpretations are generalizations of provability, and in there we can prove the generalization of the second incompleteness theorem. And moreover, having this model logic really gets us to understand what is the dynamics behind this proof in this generalized way, in the sense of Pfefferman's theorem of the non-interpretability of consistency. Right. Another generalization is in terms of definable cuts. So one may wonder that maybe a theory cannot prove its own consistency. Maybe it can prove its consistency when restricted to certain simple kind of proofs or small proofs. And well, some definitions of simple will destroy, of course, Gödel's second incompleteness theorem, but this particular one does not. And this is, if we say, if the proof, we require it to come from a definable cut. And definable cuts are definable initial subsets of the natural numbers, which are provably closed under under successor. So it contains 0, successor of 0, successor, etc. It's closed under addition, multiplication, and substitution. So if I have a Gödel number of a formula and a Gödel number of a term, then if I substitute the term in the free variable of that that occurs in the Gödel number of the formula, the resulting Gödel number should be again in my cut. And well, Buss's smash function or the omega-1 function is sufficient closure condition on cuts to be closed under substitution. So those are the definable cuts that we consider. And now we can consider, well, provability with a witness, with a proof that is small in a sense, right? Definable cuts divide numbers into small ones and the large ones. And so we can have this notion of small proofs. And well, even though the definable cuts are not sigma 1, so the provability notion need not be sigma 1, we can still prove in general the Hilbert-Bernays-Loeb conditions. And in particular, we get this generalization of Gödel's second incompleteness theorem. So a theory for a large class of theories that the theory will not prove its own consistency on a definable cut. And right, it is nice to remark that actually provability on a cut and the logics that arise by this, they play an important role in the investigations of interpretability logics. So we have seen in the previous slide that there are two prominent logics, is ILM and ILP, and they belong to different classes of theories. So the first one, ILM, corresponds to theories that are essentially reflexive or have full induction, and the second one corresponds to theories which are finitely axiomatizable and of some minimal strength. And this major open question in this field is what is the structure of principles that holds in all those kind of theories. And that's a major open question. And the logic that arises from this generalization of Gödel's incompleteness theorem provides major progress in this area. So I find this curious. Consistency on a cut can also be used to prove generalizations of Gödel's incompleteness theorems with respect to, so this sentence is not provable with a proof of at least this length, etc., etc. So these techniques, but I guess that we can see some remarks on this later in Putlak's talk, can be used to show results on, well, speed up phenomena and so forth. So this is an important generalization as well, provability on a cut. The one that I most often use in my research is this one. We have proofs with oracles, right? So very often you see in textbook that the statement for Gödel's second incompleteness theorem with respect to computably enumerable theories, but this can be generalized to theories with an oracle. So n provability here can we, for the purpose of this talk, there are many other ways of reading it, but here we will say T, a formula is provable in the base theory T, together with the set of true by n sentences as oracle, right? This notion of provability is then sigma n plus 1 for the n provability. because it says there is a formula and it's a true pi n formula, so that exists, and then pi n, and then and there is a proof, right? So of my original formula from the oracle. And so even though it is not a CA probability predicate, we still have that the Hilbert-Bernays probability, low probability conditions hold, in particular, and even stronger for a large class of theories. We have that GL describes exactly the behavior of this probability predicate. So in particular, we get this generalization of Gödel's second incompleteness theorem, that for a large class of theories, the theory will not prove its own consistency. Well, it's not a generalization; it's a weakening, actually. But anyway, it's a widening the scope, right? And an important thing is that we can, so we know that for each provability predicate of this nature, this box N, we know the corresponding logic, which is GL. But Japaritse could take them all together, all these omega many, well, omega many in the sense of all natural numbers. So GLP, he considered logic GLP, which has for every natural number a modality corresponding to this notion of provability. And he found a sound and complete axiomatization for this with respect to piano arithmetic. And it's just adding this axiom scheme. So if I know phi is consistent at level n, then I can prove it at level m, right? Because the n consistency is a pi n plus 1 statement. So if it's true, then at level m, I can use all true pi n plus 1 sentences. So in particular, I can use as an oracle. So I can use this true sentence as an oracle. So trivially, it's provable at level m, right? And the other one is the monotonicity axioms. It says if I'm provable at level n, then I'm provable at any higher level. And this is, of course, also trivial. And the beauty is that these principles, adding them to GL for all of these modalities, and having, again, as rules, modus ponens, and necessitation, generates exactly all the always provable principles for piano arithmetic. Right. So this is another generalization. So now I come to the second part, to the third part of my talk, which is, so previously the logics that we exposed had been put to work basically to solve, as in the case of Friedman's problem, to solve a generalization, a large class of problems related to the incompleteness theorem, or better understand the dynamics behind it and study its invariance to slight variations. Now, actually, when I first learned about Gödel's second incompleteness theorem, I was not surprised because, well, of course, I was struck by beauty, but in a sense, it makes sense to me that if you commit to, so the non-provability of reflection says, well, if I can prove something, that what I prove is true is not provable. And okay, I can imagine this because this somehow involves the infinite and some processes there. And so committing to the axioms of a theory is different than from committing to the consequences. But then my intuition was that so if you close off once under Gödel's second incompleteness theorem, so adding reflection, then you should be done, right? Because then you have captured the dynamics of going from axioms to theorems. But no, I mean, then you get a new axiomatizable. Of course, I now understand the mathematics, but at times it's good to just express the wonder that you perceived at first. So the bottom line is it can be iterated, right? So for a large class of theories, it can be iterated. So, for example, sigma 1 sound, CE, and extending elementary arithmetic, we have that. If I add consistency, I get again a theorem that will not prove its own consistency. And if I do that again, I will get it. So I add this unprovable statement to the base theory, then it won't prove its consistency, and so on and so forth. And this gives rise to the notion of Turing progressions. So now what we do is we use the generic form of Gödel's second incompleteness theorem and the wide applicability to get partial completions of theories. So we go add it and add it and add it. And I think that's another essential application of logic. So I see understanding the incompleteness phenomena, generalizing it, and also completion. I think those are important reasons why to study these logics. Right. So Turing progressions are such a way of partial completions of base theories. So we can iterate adding consistency. And let's do this using the generalized notion at the same time of provability. So we define, we have this sub-index for the Turing progression at level 0. So that's the sup index, and for of kind n. So in all kinds n, we define the Turing progression to be just a base theory. And then at level, at successor stages, what we do is we take the previous theory and we add the consistency. And then depending on what Turing progression you consider, you add the n consistency, the corresponding notion, right? Of course, this is all very sensitive to a representation of my of some predetermined and prefixed ordinal, because of course this statement n consistency of t should be an arithmetical statement. So it really forces you, if at least if you do coding on natural numbers, to have an arithmetization of your ordinals in the natural numbers. And this is of course the weak spot and source of many open problems in the area of proof theory. But we fix here a particular ordinal notation system and its arithmetization. And once we do this, we can define these Turing progressions where we iteratively add consistency statements taking unions at limit stages. Right, so the idea is we have a theory and we get stronger and stronger theories, and this goes on and on. And this is, one can use this method as a partial realization of Hilbert's program, so of ordinal analysis. So we can define for a theory T its ordinal analysis. There's hidden, of course, this lambda, but we in the notation we have just U and N as as indices. So given a theory T, I can define its provable its probability ordinal, proof theoretic ordinal at level N with respect to a theory U. So I take a basic theory U and I start iterating N consistency, and my proof theoretical N ordinal is just when I the supremum of all the stages that still stay within T, right? So this is an important notion. And the nice thing now is that this logic GLP, right, this polymorphic probability logic with a modality for each natural number, this is a versatile tool to speak about Turing progressions. Right, so if I iterate consistency, yeah, that's sort of clear that I can denote this by this term, diamond, m iterations of the diamond of true. So that really denotes a Turing progression. But what about the omega Turing progression, right? So I take adding consistency, and then I take the limit, the union of that. So do I have a modal term denoting this? And the answer is no, I don't. But, and this was already observed by Schmerl, I can approximate this Turing progression in the sense that the one consistency of my base theory will be equivalent for pi01 sentences to the omega Turing progression based on T. And Beklemyshev could generalize this, and he says into his result, it says for every ordinal below epsilon naught, there is such a consistency statement. Well, it's actually an iteration of consistency statement, such that adding this iteration, or the arithmetical interpretation of the iterated consistency statement to T gives me exactly the alpha Turing progression. Well, exactly with respect to pi01 formulas. Right. So this tells us that the logic GLP can speak in a sense about Turing progressions, which is beautiful and powerful. And certain reasoning in the modal logic can then be translated directly to reasoning about Turing progressions. And yeah, that's just very, very beautiful. That reasoning in a p-space logic, so relatively simple logic, can tell you things about the mathematical reality out there, namely in this case Turing progressions. So these worms, these iterated consistency statements, actually are very very powerful. So what these worms are iterated consistency statements. So for example, here we have the 4th consistency of the 11th consistency of the 14th, etc. Right, of the base theory. So we denote the set of all worms by this W, and we can order them in a sense that A is less than B if B proves the consistency of A. Right. And now the class of this set of worms under this ordering is well, modulo provable equivalence is under this ordering isomorphic to the ordinal epsilon 0. So in that sense, GLP and in particular worms can talk about ordinals, right? So we have already seen in these Beklemyshev formulations that they can talk about Turing progressions, they can talk about ordinals, and moreover now we see that right here in this statement it says for every ordinal there is a worm A, and it's exactly that worm A is given by the isomorphism stated here above, such that adding the worm to the base theory gives an approximation of the alpha's Turing progression. Now, Levant and Beklemyshev, well, Levant in first instance and generalization of Beklemyshev showed that worms can also, particular worms can be used to denote fragments of arithmetic. In particular, if I take elementary arithmetic and add the n+1 consistency of elementary arithmetic to it, then that is equivalent to I sigma n, and this can be provable in suitable meta theories. This can be proven in suitable meta theories. So in particular, we see that the theory of piano arithmetic can be generated by this filter of worms. Right. And of course, worms denote elements in a modal logic. And we also have this closed fragment of this modal logic GLP, which has a nice universal model. So and worms denote particular points in there. So worms have various interpretations, and this versatility makes versatility of worms makes them very powerful and renders major parts of the computation of proof theoretical ordinals to just an exercise in this modal logic GLP. Okay, I'd like to mention here that since we have this correspondence to ordinals, Beklemyshev was able to define a worm battle where you chop off the head of a worm and it grows back under certain rules. And of course, the worm seemingly grows, but it defines a strictly decreasing progression in the corresponding ordinals. And so then you get a principle of every worm dies, which is true, but unprovable in Peano arithmetic. So this is nice. I find this particularly nice. So now we see theorems about structures logics that describe incompleteness phenomena, that theorems about those logics themselves give rise to new incompleteness phenomena. Here's another one which I find particularly nice, also dating to Beklemyshev. So we can consider GLP minus, which is just replacing this axiom of monotonicity by a weakened version. And then it is known that each extension of this GLP minus with a set of negated worms is finitely axiomatizable. However, this itself is not provable in Peano arithmetic. And so that's nice. Logics for provability, for independence, give new independence results. Okay, so now I want to speak about minimality of certain of the logics that we have seen. So for various arguments using GLP for this ordinal analysis, we don't need a full logic, but we can work in a restricted signature. In particular, we can move to strictly positive logics, as we have seen in Beklemyshev's talk. So the signature here is the terms are given by propositional variables, truths, conjunctions, and diamonds. And reflection calculus then consists of one of such expression implies another one. So no iterations of implications, so to say, right? And then we have seen this axiomatization of reflection calculus as follows. So A proves A proves true. So this is the first line is stuff about syllogism, so to say. The next bunch of axiom and rules tells us that conjunction behaves as it should. And here we see some modal axioms stand alone that capture that if something is provable, then it's provable, and that it's provable here in the consistency form, and necessitations. If A implies B, then the consistency of A implies the consistency of B. And here we have the monotonicity axiom. And this somehow tells us that indeed small sentences can be pushed under a diamond operator. So this is the reflection calculus. This can be used without going further into details to do the ordinal analysis. So this is much simpler. In particular, we have good Kripke semantics, whereas GLP is Kripke incomplete. And moreover, the decision problem drops from P space to for GLP, which is Shapirovsky's result, to P time for reflection calculus. So which is nice. So this is minimal, in a sense, logic, or small logic. And since this logic is simpler, it allows for more general arithmetical interpretation. In particular, we can now interpret these diamonds as not only reflection principles which are finitely axiomatized, but also infinitely axiomatized reflection principles. Okay, so those are remarks that we can go simpler. We can go for GLP, we can go to simpler logics. So this was for me a motivation to study the following question. If we have a drop from complexity from the full fragment to a strictly positive fragment, maybe we can do something in the realm where everything seems bad, namely quantified model logic. Well, briefly repeat some items from Kurahashi's talk. So what is the game in quantified model logic? We now have predicate logic with modality, and then we translate them to formulas of piano arithmetic. I take up some extra time because we started 5 or 7 minutes late. So what we do here is the same game. We translate for all x to for all x and the box to the box. And now the n-ary relation symbols will be translated to formulas with n-free variables. And then one can define, right, the quantified provability logic of a theory is now, again, the collection, but now in this signature of formulas, which is always provable. And the true quantified probability logic is the set of formulas in this signature, which is always true. Right, for example, this is a formula which would be always provable. If provable for all x p, then, right, then we have also for all x provable p of the numeral substituted for that x in p. Right. Now, there are some degenerate quantified probability logic cases. For example, if we take no modality, then we just get predicate logic, which is quite easy to see. If we add inconsistency of piano arithmetic, then the quantified probability logic is also recursively enumerable. Namely, it's just classical quantified calculus together with Box-Walsen. But basically, anything else seems to be just exploding. And these are the famous negative results by Vardanyan, Archimov, and Montagna. So we know that always provable sentence is Pi2 complete, and always true is not even arithmetical, it's Pi1 complete in true arithmetic. And we have seen in the talk by Kurahashi that these results are really robust. So even Vardanyan could prove it where no iterations of modalities and just one unary predicate symbol is already Pi2 complete. And that seems to imply that already this logic is also will have a Pi2 complete quantified probability logic. We have seen that from a result by Berarducci in Italian that if we take restrictions to sigma 1 sentences, we still get Pi2 completeness. And Visser showed us that the base theory can be taken much. Visser and de Jonge showed this. So they published a paper, No Escape from Vardanyan's Theorem. And well, as a student of Albert Visser, it was of course a great pleasure that I'm now about to publish a paper by the title An Escape from Vardanyan's Theorems. A preprint is already up on the archive. There was already a minor escape known by Archimov and Japaritse. So in particular, formulas refutable in finite models, Kripke models can be, that fragment is decidable. However, this is not nicely syntactically characterized. It has a consequence which has a syntactical characterization, is the one variable fragment. So the thing that we do here is we go we go to the strictly positive fragment. So I think I should speed up a little bit. So what I do, I'm going to present the logic. Here it is. So the logic is given by these axioms. So the leftmost collection just deals with reflection calculus as before, nothing new. And then we have the model operations as before, also in reflection calculus. And now we have the obvious rules for universal quantification. Right? And the thing is that this gives us an escape from Vardanyan's theorem. Maybe I should stress that now this formula comes from the fragment which only allow relation symbols, the top conjunctions, and now we take infinite conjunctions, which is universal quantification, and diamonds. And as before, now we get a decidable fragment, which is beautiful because we have a drop from Pythocomplete all the way to decidability in the logic. So let me skip a little bit about the semantics and go to the main theorem. It says that QRC1, the logic that we present, really captures all the consequences of this form. So if I can prove that phi entails psi, then the theory axiomatized by psi is provably conservatively extended by the theory extended by phi, right? And that's expressed here by this Pi2 sentence. Okay, I will not go into the proof, but it's a straightforward proof by induction applying the known arithmetic. And the completeness proof, we could also do this recently. And so we have now a complete decidable fragment of quantified probability logic. What should be mentioned here is that indeed the logic, because reflection calculus has slightly different semantics in the sense that it refers to theories, but it can be related to exactly a fragment of quantified probability logic. And indeed, this is a nice drop. The upper bound is doubly exponential, but I think we can get it much lower, the decidability for QRC1. And our advanced conjecture is that it works for HA as well. Now, we already mentioned that closed fragments are good in the sense that they're also minimal because, for example, Friedman's problem, we don't need full Gödel-Loeb's logic. We can go to the closed fragment, and as we have seen, we saw the decision procedure, that's P time. And this is what we see as well. So if you go from full to a closed fragment, then you also get often a drop in complexity. In GLP0, the situation is slightly different. You stay P space complete for the full closed fragment, but if you only are interested in deciding n fixed number of modalities, then it's P time. And something similar happens in interpretability logics. So that's good as well. So interpretability logic for M0 and P0, they have P time decision, whereas various interpretability logics are known to be P space complete. And it's curious to remark that IL0 still remains P space complete, but it's not arithmetically that much interesting, the closed fragment of IL. Okay, then I just wanted to mention that sometimes closed fragments are not sufficient, but then you can add constants. And for example, I have some biased examples here in calculus to denote Turing progressions by adding constants for ordinals, or constants for I sigma 1, and then you can find a logic that decides all questions of this form. So, for example, I sigma 1, does it interpret P array plus con P array? Does con P array interprets this, etc., etc. So these are natural questions, and then there is a simple logic that decides all of them, very much in the style of Friedman's question. Okay, I want to finish this talk by having a simplification of a simplification. So we already saw that RC is a simplification, the reflection calculus of GLP. And now we can do a second step on that, and we can go to the closed fragment of it, and which is surprisingly enough still sufficient for a large part of the computation of the ordinal analysis. And here we can even dispense with conjunctions. Right. And this is a result by my student Anna Borges and myself. We have the worm calculus, which is given by this very simple calculus and of very good decision properties. So, and that brings me to the end of this talk. I wanted to show logics for incompleteness, what we can do with them, and show various generalizations of them, and then how we can narrow them down, throw away pieces we don't need to get simpler and simpler logics. Thank you for your time and interest.